Like, I need to be concentrated, or else I'm not gonna get this stuff.
First of all, your assignment, if you haven't submitted the assignment now, please remember to submit it at the end of the lecture. Even if you made some partial progress, even if you haven't done all the problems, submit something. We have a new assignment due next Friday. So here all the assignments will be due the lecture on Friday. You'll see the next assignment is somewhat different. We have 3 problems, and not only the answer to each one of the problems should be written in full sentences which are readable and understandable. The questions will be somewhat more qualitative than quantitative. So the answers will not be just numbers or not just equations. They will be equate explanations. So one of the questions will ask you something like, how would it feel to experience a constant jerk? And the jerk will be explained in the problem what it means. And the answer will be, well, it feels like, and then some explanation. So you see it's more qualitative, it's probably somewhat different from what you are used to in classes. Good try it, it should be an interesting experience. Okay, so in the end of last class we discussed the notion of average velocity. So we talked about let's say if you have a car and you find out that the car moved, say 100 kilometers during the time span of 2 hours, then you know that the average velocity of this car was 100 divided by 2, which was 50 kilometers per hour for the span of these 2 hours. And we discussed in the end of the last class that it doesn't matter how it moves in between. It might do most of this movement in the first hour, but go with speed of 100 kilometers per hour in the first hour, and then just rest for the other hour. Still, the average velocity is 50 kilometers per hour. So I'll remind average velocity is f of t denotes the position of an object at time t. So this function f of t is a measurement. It measures what is the position of my object at time t. If I know, well, I first of all choose some kind of coordinate on the line. I say that somewhere is 0, somewhere is, well, I fix some scale, for example, I measure it in kilometers, and I say this will denote the distance to 1 kilometer. And then for each time t, I know what is the position. Let's say at t equal to 0, I know that the car is located at 2 kilometers from the origin, so here is the position at time 0. Then I know that it moves like to the right, and I know that in an hour it will be at 10 kilometers, so in an hour the position will be somewhere here. The question is, what is the average velocity? So I fixed 2 moments of time, t1 and t2. What is the average velocity during this period of time? Yeah?
The change in distance over
Okay.
the time?
Exactly. So it's change in distance, so we call it displacement over the, well, time span, time that passed, which in formulas would be like this. The displacement, how much the position changed, is the difference between the final position and the initial position. Change in time, well, it's the difference between final time and starting time. And that's the average velocity. Once again, it does not matter how the object was moving from T1 to T2. So it could have moved, let's say it moved, so this, let's say it's x of T1, and let's say it ended up being here, x of T2. It doesn't matter whether it did something like this, move really fast and really slow, or really slow and really fast, or slow, fast, slow. It doesn't matter. As long as it moved from here to here in some particular period of time, T2 minus T1, the average velocity is given by this. For example, let's say we have a car which moved from, let's say, 9 o'clock. At 9 o'clock it was position 100, and at 11 o'clock it was position 200. Then average velocity from t equal to 9 to t equal to 11 is, and I just use this formula, the displacement 200 minus 100 divided by total amount of time which passed. So 100 over 2, 50. And depending on the units of measurement, we'll have a unit of measurement here. So x is in, say, kilometers, and t is in hours. Average velocity is in, well, the numerator is measured in kilometers, the denominator is in hours, so overall it's in kilometers per hour. Alright, so this is the notion of average velocity. Let me interpret this notion geometrically. So let's say I'm starting a new example, not related to this one, so it's a new discussion. Let's say I give you the position of the car, the position of the object, not using some data like this, I don't give you the function, I give you only the graph of this function. And let's say that's the graph. So we see at time t1, at time t2, we have this position, this will be x of t1, this is going to be x of t2. We see how the position is changing. So you should imagine that time goes kind of uniformly, but the position is obviously changing faster here than it does here. Well, what is this notion of average velocity on this graph? Let's look. Where do we see this thing, the numerator, x of t2 minus x of t1? Do we see it on the graph?
Yeah.
Yeah.
It's the slope between the point x of t2 and t2 and x of t1.
Okay, so yes. Basically, yes. So let me do it slower. First of all, just this distance, x of t2 minus x of t1. It's exactly this distance. It's x of t2 minus x of t1 is this distance. So this distance is exactly x of t2 minus x of t1. The denominator, t2 minus t1, this distance, t2 minus t1, is this thing. quotient, this over this. Well, we've seen such a quotient, kind of the rise over the run. So if we connect these 2 points by a straight line, maybe let me use the power to this additional line. It's not describing how the car was moving, it's just an auxiliary line. It's helpful to us. It does not mean anything about the position of the car. But its slope is x of t2 minus x of t1 divided by t2 minus t1. So rise over the run. Now, what is the meaning of this line? So first of all, we understand geometrically how to find the average velocity just by looking at the graph. We connect the 2 points by a line. Its slope is exactly the average velocity. Well, but what is the meaning of this line itself? So, imagine that there was a second car which was moving according to the equation which is described by this function, so the straight line. What can we say about this car?
The speed is constant.
The speed is constant, exactly. So the rate of change of the position with respect to time is constant. It's the same here, it's the same here, it's the same here. So this car, our original car, was moving, well, in some funny way. It was going faster here, so the position was obviously changing faster here, then it was changing here. This one, no, it moves with a constant velocity. So this notion of average velocity is like this. Suppose I have an object which moved, well, from being here to here, from one place to another one, during a time span of t2 minus t1. If there was another object which is moving with a constant velocity, what would this velocity be? And well, it moved from the same place to the same destination during the same period of time. So this is the movement of an object with constant velocity, and the slope of this line is the average velocity. So let me write down what we found. So on a graph versus t, one thing, straight lines describe objects moving with constant velocity. Another finding, the slope of such a line which connects 2 points on the graph is called the secant line for a graph. Or the secant line through points t1 x of t1 and t2 x of t2. So we have 2 points like this. The slope of such a line is the average velocity. From t1 to t2. Great. So now we have a way to just look at the graph and decide something about the average velocity of objects. Let's look at this graph once again and ask ourselves some interesting questions. So here's a graph which describes movement of some object. What can we say about this object? Let's say I think about this as well. Let's say we are in the same situation. A car which is moving for a period of 2 hours. Was it moving faster on average during the first half of the trip or the second one? Yes. First one. Okay, second one. Alright. So what is the meaning of this question? First of all, what does it mean half of the trip? Well, to be honest, it can be interpreted in 2 different ways, and it's probably why I got different answers. When I said half of the trip, I mean the half of the time of the trip. So not half of the distance to destination, but rather half the time to destination. So somewhere is the middle point in our trip. Half the time is already passed. Well, let's look at this graph. So we are somewhere here. In intuitive terms, well, it looks like we already are past, well, we did more than half of the trip already in terms of distance. So we already covered this distance and we still have to cover this distance. So obviously in this first half we moved more. So the average velocity must have been higher. Geometrically, in terms of our knowledge of what average velocity is, we just have to compare these two slopes. This slope is the average velocity for the first half of the trip. This slope is the average velocity for the second half. Which one is higher? Well, obviously this one is higher. So here, the car was moving on average faster than here. Alright. So let's ask other questions. Let's say I'm interested, in a car, you can see at what speed you are moving. You have a device which shows you are moving at 60 kilometers per hour, or you are moving at 75 kilometers per hour. What does it measure? What does it actually measure? So here we talked about average velocity. The thing that it measures is, well, not the average velocity, but actual velocity. How fast you are moving at a given time. So it gives you feedback as you look at it, not after one hour has passed and it measures the average velocity, but the velocity at a given moment. So let's say I'm talking about the same car. And now I'm interested in the reading of this device which shows the speed. Let's say also somewhere in the middle, so somewhere here. So what kind of number would it show? First of all, I didn't give you any point of information, so I didn't give you the actual numbers here. So my question is somewhat meaningless in terms of I don't expect a number. But I do expect to understand eventually what is the meaning of this number, which I see on the reading of this. What is the speed at the moment? Not the average velocity, which we kind of understand displacement over the time, but a speed at the moment. Yeah.
Slope of tangent
Okay, why slope of the tangent? That's the correct answer. Why?
as it approaches it from both sides. It's more prolific.
Okay, yes. So the idea here is like this. Well, if we measure the average velocity from here to here, from T1 to T2, it's not quite the same as the velocity here, because we know that the car was moving a little bit slower for the second part than it was for the first time. So such a slope, well, it has something to do with the velocity at this point, but not quite. it's just the average velocity during, let's say, the whole span of 2 hours. Can we get any better? Well, yes, let's measure the average velocity, but on a time interval which is really closer to this point. So let's say I measure the velocity from here to here. The average velocity, still the average. I'm going to get a different number, not necessarily the same. But it's going to reflect a little bit better what happened at this particular moment. Because instead of measuring the average velocity during the time period of 2 hours, I'm measuring it, say, 1 hour. Why stop at 1 hour? Let's make it the average velocity during the period of half an hour, 5 minutes, 1 minute, 1 second. Eventually we'll get better and better approximations to the velocity at this particular moment. So if I measure the average velocity during 1 second, it's reasonable that the actual velocity didn't change that much during this 1 second. So instead of measuring this slope, I'll measure this slope, then let's say such a slope, such a slope. Each next slope will be a better and better reflection of what is the velocity at this particular moment of time. Eventually, so I see such a line, such a line. I make this time interval really, really small. I'll get lines which are close to the tangent line. So exactly as we said. So just a line which barely touches this graph, not intersects it at 2 points in this neighborhood of this point which I'm interested in, but rather barely touches it. And its slope is going to be the velocity at this particular moment. So slope tangent is instantaneous velocity. So let me talk about this instantaneous velocity. So I'll say something like this. When T2 is close to T1, the average velocity x of T2 minus x of T1 divided by T2 minus T1 is an approximation of the instantaneous velocity at time t1. So if I take a really short period of time and measure the average velocity during a really short period of time, my answer is going to reflect how fast I was moving at the time t1. And on the graph, we just looked at this picture and we realized that on the graph of t, x is a function of time, the instantaneous velocity at time t1 is the slope of the tangent line.
Is the tangent also the derivative?
So we'll get to this concept of derivative, but for now I assume that most people haven't seen it.
Okay.
The answer is yes, the slope is the derivative, but we'll talk about it later.
Okay.
Other questions? Okay, so now we know two concepts of velocity. One is the average velocity during a period of time. Another one is a reflection of how fast an object is moving at a particular time, which is the instantaneous velocity. So let's solve for example, let's say example. Let's say f of t is t squared minus 4. What is the instantaneous velocity? Time t equal to 2. So I have an object. Let's imagine how it moves. T, x. So t squared minus 4. At point 0, it is 0 squared minus 4 is minus 4. Time 2 is at 0. Time 1 is at negative 3. In general, it's kind of parabola. We know that x equal to t squared will be a parabola like this. Now we have a transformation of the graph, t squared minus 4, so we shift the graph like 4 reads down. And let's say we talk only about the positive times, so only talk about this thing. So this is 0, this is 1, this is 2, this is negative 4. And the question is, how fast is the object moving right here? So, okay, let's try to understand this. So the idea would be to try to use this definition, well, not definition, but rather observation. The measure of how fast the object is moving at time t equal to 2 can be approximated by finding average velocities on shorter and shorter intervals, time intervals around this point t equal to 2. So let's say I'll make a table. I'll choose some period of time t. I'll compute x of t minus x of 2 divided by t minus 2. That will be the average velocity from 2 to t. And then we'll see, well, what happens. We'll see when these things actually approximate some number better and better as t becomes closer and closer to 2. So let's start with something, let's say 3. What is the average velocity of this particular object as time goes from 2 to 3, so during 1 second? Let's see. X of 3 is 3 squared minus 4, 5. Minus x of 2, 2 squared minus 4, 0. Divided by 3 minus 2, so it's 5. What we just found is that during this 1 second, from t equal to 2 to t equal to 3, the object was moving at average velocity of 5. Well, something I didn't tell you what the units are. So let's say x is in meters and t is in seconds. then it will be 5 meters per second. It's good, it's some approximation to how fast the object was moving at time t equal to 2. But it's probably not exactly the answer. It looks like the object is moving kind of faster and faster. The position is changing more and more as we go to the right. So it looks like our actual answer will be smaller. Okay, so let's try something. Let's say 2.5. Instead of measuring the average velocity for the whole second, let's restrict ourselves to half a second. The answer, 2.5 squared is 6.25 minus 4, so 2.25 minus x of 2 is already computed at once, 0, divided by 2.5 minus 2. So it's 2.25 divided by 1/2, 4.5. Well, indeed. So during the first half of the second, the object was moving on average a little bit smaller, around 4.5 meters per second. So this is a little bit better approximation to how fast the object was moving at the point t equal to 2. So why take the whole half second? Let's take 1/10 of a second. Let's make it 2.1. 2.1 squared is 4.41 minus 4, so it's 0.41 minus 0 divided by 2.1 minus 2. Well, the answer is 4.1. So during the first 1/10 of a second after the moment t equal to 2, the object was moving on average with velocity of 4.1 meters per second. Well, why stop here? Let's make even more precise measurement. Let's measure the average velocity for 100 of a second. 2.0. Okay. So 2.01 squared is going to be 4.0401. So minus 4 is going to be 0.0401 minus 0 divided by 2.01 minus 2. So it's going to be 4.01. So during the first 100th of a second, the object was moving with the velocity of average velocity of 4.01 meters per second. So in real life, if we actually had a measurement and we actually had like equipment to measure the position at time t equal to 2, then t equal to 2.01, well, we'll eventually reach kind of the limit of our measurement device. Maybe our measurement device can only measure 100th of a second, and then this would be our best guess of what is the velocity at the point t equal to 2. In mathematics, we are not restricted to actually using measurements, actually using some devices. We can imagine that we make more and more precise measurements, and we don't have to stop anywhere. We can go to 2.00001 if you want. Well, this is going to give you a quotient of 0.000040001 divided by 0.00001, 4.00001. So during the first 1/10,000th of a second, after this moment t equal to 2, the average velocity was 4.00001. Can I try to guess what the velocity was at the moment t equal to 2? Yeah. 4, yes. It looks like the more fine our measurement is, the smaller we take this interval, the closer our answer gets to 4. So if we were actually physicists and we actually made a we would probably just forget about this small rounding error. We just say our velocity was 4. Well, geometry magicians, we don't just throw things out. We imagine that we make more and more precise measurements, and our answers get closer and closer to the actual answer, which is 4. So instantaneous velocity is 4. Incidentally, we also solved. Yeah.
We get like actually like right on 4, right?
So we never will get actual 4. So if you take, well, you can't take 2 exactly because there is no movement from 2 to 2. So you can't actually take t equal to 2 in this process. But you can get really close to this number 4. In fact, if you want to get this 4 up to, let's say, 4.0000000000001, well, just take enough zeros here. But you will never actually get the 4. But you'll get as close to 4 as you want. Okay, so incidentally, we also solved a somewhat complicated geometrical question. What is the slope of the tangent line of this graph at the point 2? Well, from the picture, it's not that obvious. But we just argued that the slope of the tangent line is the velocity. You compute the slope by exactly the same process. So we kind of interpreted this as average velocity from 2 to t. It's also the slope of secant lines from 2 to t. So secant line from 2 to 3 has slope of 5. Secant line from 2 to 2.5 has slope of 4.5. From 2 to 4.1 has slope of, 2.1 has slope of 4.1. The actual tangent line has slope 4. Also, slope of the tangent line the graph x of t at t equal to 2 is 4. Okay, so questions about this thing. Maybe to motivate you a little bit, such functions, quadratic functions of time, appear all the time when you measure movement of foreign objects on it. So at the beginning, the object barely moves, but then its velocity increases and increases and increases. And the position, if you measure the position, it turns out is a quadratic function of the time. So right now, well, if we were in actual physics class, we would have answered some kind of meaningful question about the foreign object. If you measure the position, it's given by this class, how fast the object hits the floor. Let's say position is 0 means floor. We measure the distance from the floor, well, that's how fast. Okay, talk about some different kind of question. So another question, given the graph of t, sketch the graph v of t, which is the velocity at time t. So this kind of question is, we have regions called, I know, GPS from the car. So you know the position of the car at every moment of time, and the question is how fast the car was moving. And I'll give you the graph of x of t. So here is t, here is x, and the graph looks like this. The question is, well, what can you say about the velocity of this car at every given moment of time? So first of all, let's just look at this graph and try to imagine what was happening here. So I didn't give you any numbers, I didn't even tell you what the scale is. But still, I can try to imagine roughly what happened to the object. So in the very, very first and crude approximation, what happened was like this. From here to here, so I have some interesting moments in time. From here to here. Well, in the most crude approximation, the object moved to the right. Let's say I have this x-axis is in this direction. How can I imagine the movement of my object? Well, somewhat like this. I had an object here, then after some time has passed, the position increased, so the object has moved to the right, from here to here. Then, for some period of time, the position was not changing at all. So the object moved to the right and then stayed in place. Didn't do anything. Then it kept moving to the right. The position kept increasing. Then it started moving to the left. The position, the distance from the origin, starts decreasing. And eventually it passes even to the left of its origin, so something like this. So just by looking at this graph, I see, well, in very kind of rough approximation, what happened to my object. It moved to the right, stopped for some period of time, then continued to the right, then turned and moved to the left. Well, but actually I can give much more precise information about what was happening to this object. How? No, I know that the velocity is actually visible from the graph. It's just the slope of the tangent line. So all I have to do is estimate what the slope is at each point on this graph. So, it's not that hard. So here I see the slope. Once again, I do not have any kind of scale here, so I can't be precise numerically, but I can be precise qualitatively. So here I see the slope is pretty high. In fact, one of the highest slopes of the tangent line on this graph. So I start somewhere high on my velocity graph. At the very first moment of time, the velocity was pretty high. What happens as I go from here to here? Well, the velocity is always positive in the slope of this graph. The tangent line always goes up. But I see that it becomes smaller and smaller. So here I have a steep tangent line. Here I don't have a tangent line which is as steep. So I'll draw some kind of graph. Well, to To what extent does it decrease? At this point, what is the slope of tangent line? 0, exactly. So here, my graph becomes horizontal. So the tangent line to this graph has slope 0. So in fact, during this time, my velocity dropped from being, well, positive to being actually 0. And from here to here, my velocity will still 0. During this whole period of time, x is not changing, the graph is horizontal, tangent lines are all horizontal, slope 0. So I draw a line at 0. Well, let's continue. I keep moving to the right, and my velocity keeps increasing. In fact, it increases more or less up to here. So here, the slope of the tangent line seems to be the largest. If I keep moving to the right, it will only become less and less steep. So from here, the velocity is increasing up to a point. In fact, well, this slope and that slope seem to be roughly the same. Depending on the details, one is larger, smaller. But let's say I go to here. Then from here to here, the velocity keeps decreasing once again, because the slope of tangent line is decreasing. What is the slope at this point, at the peak? 0. The tangent line is horizontal. So it decreases all the way up to 0. From here, it keeps decreasing. In fact, it is actually negative, because my tangent line now points not up, but rather down. So my velocity is now negative. Okay, so I'll draw a negative velocity. It becomes more and more negative until it looks like it stabilizes. So the tangent line here has more or less the same slope as the tangent line here. So I draw a graph which decreases and then stabilizes. So now we can imagine what happened. My velocity was high, then I eventually slowed down, then I stopped for a moment, then the velocity kept increasing, then it decreases, and now it starts moving to the left. So that's the movement of this whole. Alright, so see you on Monday.